Today's lecture is going to cover inequalities and convergence of random variables. Before we start with that, however, I want to introduce a useful concept for talking about independence, and that concept is the concept of an indicator function. And an indicator function is just going to be a function that indicates whether or not something is true. So typically we'll denote it with a bold 1, and we'll say bold 1 of some statement, and this is going to be 1 if the statement is true, and it's going to be 0 if the statement is, of course, false. And so this indicator function indicates or gives a 1 the truth of the statement. So it just gives a 1 if the statement is true and a 0 if the statement is false. So for example, we could write indicator that x is in some set A, and this will just give us 0 if x is not in A, and 1 if x is in A. Sometimes this is denoted, an alternative notation here is people write 1 sub A of x. And indicator functions are very useful for writing the PMFs or PDFs of a probability distribution. The reason being, if we look at, let's say, the PDF of a random variable x, typically what we'll do is we'll write something like f of x is, well, let's just say in this example, let's say x has an exponential distribution with some parameter lambda. We would write the PDF. Typically, we would write it as, say, lambda e to the negative lambda x. And this is true when x is bigger than 0. And so to be technically correct, we have to say it's 0 when x, let's say, is less than or equal to 0. And so we really don't want to have to carry around this kind of statement that x is 0 not in the support. We really just want to kind of specify things in the support, so typically we'll leave off this second case of our kind of piecewise function here, and we'll just specify the case for the support where the thing is positive. And so oftentimes we're very loose, and we'll just write things like, we'll write, say, f of x is equal to lambda e to the negative lambda x, and it's understood, and maybe we'll say that this is true for x bigger than 0. It's understood that that it's 0 everywhere else. And basically, because we don't have to carry around this case by case statement. We could use indicator functions to solve this. And in particular, we could write the whole PDF. Instead of having to break it out into two cases like we do up here, we could write it as one statement, f of x is lambda e to the negative lambda x, times the indicator function, where x is bigger than 0. So this is a way to write the PDF as one line. The reason these are equivalent is because this indicator that x is bigger than 0 is just going to be 1 when x is bigger than 0 and 0 when x is less than or equal to 0. So by multiplying by this indicator function, what we'll get is exactly what our PDF is, lambda e to the negative lambda x times 1 when x is bigger than 0, and 0 times our PDF, which is just 0, when x is less than or equal to 0. So the indicator function here is a really useful piece of notation because it allows us to exactly write our PDF in one line. So it gives us a very powerful notation. And if you take a course like 452, these are used all over the place. So why do we care about this? We've gotten this far in the course kind of avoiding these. But the reason they're useful is when we're talking about independence. And we have this theorem, and the theorem says that x is independent of y if and only if the joint fxy can be written as fx times f of y. And this statement, as stated, is exactly technically correct. The problem is, when we have a random variable with some support, we then have these kind of piecewise functions, and we have to figure out what does it mean to multiply two piecewise functions. And so you have to very carefully think about what that means. You kind of have to think about what is the support of these random variables. And so one way to avoid that problem is to exactly write the support of the random variable using the indicator functions. So, for example, if I have a joint PDF fxy that is e to the negative x times e to the negative y, let's say for x bigger than 0 and y bigger than 0. And I want to know, is x independent of y in this case? I have to apply my theorem, I have to factor this. And so it's really tempting to factor as e to the negative x as fx and e to the negative y as f of y, but this doesn't kind of fully account for the support. How do we know that you can kind of do this factoring correctly? How does the support play there? So the way to avoid that problem is you could write fxy is e to the negative x, e to the negative y, and then to encapsulate the support, I could say indicator x bigger than 0 and y bigger than 0. The useful fact about indicator functions is that indicator of some statement A and some statement B is the product of the indicators. So it's the product of the indicator of statement A times the indicator of statement B. So I can rewrite my joint PDF as e to the negative x, e to the negative y, indicator that x is bigger than 0 times the indicator function, it's supposed to be a 1, indicator that y is bigger than 0. And now it's very easy to see how I do my factorization. I can factor e to the negative x indicator x bigger than 0. That's my f of x, and I can multiply that by e to the negative y indicator y bigger than 0. And this is my f of y. And I see that this first thing depends only on x. The second thing depends only on y. And so we're all good. Now, this example is pretty simple, and you might have looked at the support and said, well, the support looks nice enough, so it probably works. You can make a harder example. So example, what if my support fxy were some constant, which we don't particularly care about, times e to the negative x times e to the negative y, but now we have some more complicated support. Let's say 0 less than x less than y less than 1. Okay, maybe that's my support. Now you still might think, oh, I can factor it to e to the negative x and e to the negative y, and so x and y with this joint PDF should be independent, but can I kind of factor that support? And the answer is no. And so one way to see it is that if I wrote my joint PDF here using an indicator function, indicator 0 less than x less than y less than 1, there's no way to factor this indicator function into a product of an indicator function involving just x and an indicator function involving just y. And so there's no way to factor, so x is, we'll say, not independent of y because I cannot factor the joint as the product of the function involving x and a function involving y. And the reason I can't do this is I can't kind of split up this. It's not an and statement, so it's not a product of two things. So in kind of more advanced courses in probability, this is how you think about it, because it allows you to encapsulate. You will typically write, say, a PDF like this, because it allows you to write it all in one line. You don't have to worry about case-by-case basis. You don't have to write it out case-wise or piece-wise, and so you don't have to think. So it kind of allows you to keep track of the support in a very natural way. And remember, the support does matter for things like factoring independence. So, so this theorem here is kind of technically correct about independence. You just have to keep in mind that you still have to be able to kind of factor the support in a reasonable way. And what does that mean? Well, it means if I write the support as these indicator functions, in this example here, I can factor, as I showed, I can factor the support as the product of two indicator functions, and so I can factor the joint PDF, and so in this case, x is independent of y. In this case, you can't do that. It's not an and statement, and so there's no way to factor it. So x is not independent of y. And in general, you can always write, let's say generally, you can play this game with any PDF or PMF. You can always write f of x has some form times the indicator x is in whatever my support is. So you could always tack that on. That's just going to say it's whatever I choose when I'm in the support, and it's 0 everywhere else. So these ideas might be useful, and they certainly are when thinking about independence, because it allows you to encapsulate that support in a precise, rigorous mathematical way. Okay, so that's our short little jaunt on indicator functions, and so it's really useful, in particular when thinking about independence in this course. You can kind of avoid them if you don't like them. For this course, if you go on to more advanced kind of stats and probability, they're unavoidable. But I think in general they're kind of very useful concept. So that's just a useful piece of advice. The real topic today, that we want to talk about, is we want to talk about inequalities of random variables, and that will lead us to talking about convergence of random variables. So inequalities. And there are some kind of really useful and basic inequalities that everyone should know about random variables. And the first one that we want to talk about, so this is a theorem, is called Markov's Inequality. Inequality. Okay. So Markov's inequality says if I have some random variable x, and x is a positive random variable, so this means that the support is some positive set of the real line. And we're going to denote it like that. So it's a positive random variable. Then if I choose any number a that is also, say, positive or non-negative, it is true that the probability x is bigger than a is less than or equal to the expected value of a, expected value of x, over a. Okay. That's the statement of the theorem. And this is a really remarkable theorem because this is true for any positive random variable. We can relate the probability, kind of the tail probability of being bigger than some value a, to its expectation. And the picture you could draw would look something like this. Here is, I can draw my, let's say, PDF. So here's my PDF fx over x. If I choose some value a over here, and I want to look at the tail probability, so I want to look at the probability I'm in this tail. So it's kind of the area under that PDF there. This area is less than or equal to the expected value of x divided by a. It's actually not too bad to prove this theorem, and so we're going to look at a quick proof in the continuous case. Okay, and so the proof, we're going to start by looking at expected value of x. And expected value of x, we know, in the continuous case at least, is we integrate x times our PDF dx over the whole real line. Of course, in this case, our random variable is positive, so really we can just integrate 0 to infinity of x by fx dx, because our support is positive. And I can break this up, so let's continue on to the next line. I can break this up into the integral from 0 to a of x fx dx, plus the integral from a to infinity x fx dx. And because if I look at, I'm integrating over a 0 to a in this first one, so x is non-zero in this first integral, and certainly f of x is bigger than or equal to 0. This whole integral is also positive, which means that if I remove it, so it's some non-zero value or some non-negative value, I could remove that and change my equality to an inequality and say this is bigger than the integral 0 to infinity fx dx, right? Because all I'm saying is that I have a first integral, let's call it capital A, a second integral b, and all I'm saying is that a is bigger than or equal to 0, so a plus b is bigger than or equal to b, right? And so this is now b. So I can say that some of these two integrals is bigger than just one of them. They're both all positive, that's okay. And furthermore, I'm integrating on an interval from a to infinity. And so I'm integrating x times f of x on this interval. So let's say when x is in this interval from a to infinity, that is the same thing as saying x is bigger than or equal to a. And so I can furthermore, I could replace x in my integral with something larger than x, and I can say, well, it has to be bigger than this, right? X is bigger than a, so if I just replace it in my integral, the top first integral here must be bigger than the second one because all I'm doing is replacing the x with something that's smaller than it. Or something that's smaller than it, right? So, okay, so I can do that. And of course, a doesn't depend on x. I can factor it out. That's a integral from a to infinity fx dx. And this is a times our probability that x is bigger than a, or bigger than or equal to, let's say. Doesn't matter if we continue this. And so if we look at our chain here, we have a times probability x is bigger than a, and we have expected value of x. And so our statement, if you follow the chain of equal sign and inequality signs, so this says that expected value of x bigger than or equal to a times the probability that x is bigger than or equal to a. Or I can rearrange this and say that the probability x is bigger than or equal to a is less than or equal to its expectation divided by a. Okay. And that was exactly the statement of Markov's theorem that says that probability x being bigger than, you could say bigger than or equal to bigger than, for continuous doesn't really matter, is always less than or equal to the expected value of x over a. So Markov's theorem is, in and of itself, not always directly the most useful theorem, but Markov's theorem allows us to prove a more useful theorem, and that theorem is called Chebyshev's Inequality. And Chebyshev's Inequality says that for any random variable x, if we say mu is the mean of some random variable x, and sigma squared is the variance of x, then the probability of the absolute value of x minus mu over sigma, probability that is bigger than or equal to some value k, is less than or equal to 1 over k squared. And so this x minus mu over sigma looks a lot like what we call a z-score in an introductory statistics course, and it basically is. The proof of Chebyshev's is really simple once we prove Markov's, so that's why I proved Markov's first. The use of Chebyshev's we'll see, hopefully we get to see in some of the topics of convergence. So it gives us a bound, and we'll see how that's useful for convergence. But the proof of Chebyshev's is not so bad. If we define y to be, let's just take x minus mu squared over sigma squared, and we let a be k squared, you notice that y is a positive random variable. It's a squared, so it better be positive. So by Markov's inequality, if I look at the probability that y is bigger than or equal to k squared, this should be less than or equal to the expected value of y over k squared. And then I just have to convince you of a couple things. One, expected value of y is the expected value of x minus its mean squared over its variance. I can pull out that variance. It's 1 over sigma squared times the expected value of x minus its mean, which we can write as the expected value of x squared. And this is just, by definition, this is variance of x, which we define to be sigma squared. So this whole thing is equal to 1. So the expected value of y is by construction 1. So that allows us to say that the probability that y is bigger than or equal to k squared is less than or equal to 1 over k squared. And from there, we just have to fill in for what y is, or probability y was x minus mu squared over sigma squared, bigger than or equal to k squared, less than or equal to 1 over k squared. And I can certainly say, or I could take the square root of both sides of the statement in my probability. So I could say that the probability, if I take the square root of x minus mu squared, I get absolute value of x minus mu over sigma, bigger than or equal to k, or assuming k is a positive number, less than or equal to 1 over k squared. So this is the first form of Chebyshev's inequality, which is what I wrote. And one way to think of Chebyshev's inequality is that if I have a picture, so here is my PDF or PMF, and I look at the mean, so maybe my mean is here, and I can look at some number, basically the probability. If you read the statement, it's that if I look at, this is like mu plus k times sigma, and this is mu minus k times sigma. The probability on outside of more than, so either the left or the right, k standard deviations away from my mean is less than, so the probability of being greater than or equal to k standard deviations away from the mean is less than or equal to 1 over k squared. And as I increase k, the probability of being in that tail behavior, that tail of my distribution, drops off very quickly. And this is an amazing result because it doesn't depend on any, it doesn't depend on normality, it doesn't depend on anything except it being a random variable. So it's applicable to everything. And it gives you a bound of how much probability can I have in the tail of my distribution. There are other ways that we can write Chebyshev's inequality. So let me just write various forms of it. So one, as I said, the probability of x minus its mean, absolute value over sigma is less than or greater than k, is less than or equal to 1 over k squared. Other ways I could look at the complementary, the probability that x minus mu over sigma is less than or equal to k is going to be greater than or equal to 1 minus 1 over k squared. So basically subtract, taking 1 minus on each side. I mean, need to flip my inequality, and I get a 1 minus 1 over k squared. Those are complementary. So this says the probability being within k standard deviations, what I mean, is bigger than 1 minus 1 over k squared. It's going to be at least 1 minus 1 over k squared. And some other useful forms. I could define. So let's see. How else can I think about this? I can define epsilon to be k times sigma, and so then Chebyshev's inequality would say that x minus mu greater than or equal to epsilon is less than or equal to. So if epsilon is k sigma, then k is epsilon over sigma, and 1 over k squared is sigma squared over epsilon squared. So we could say it's this, that probability. So this is kind of the third useful form. So we got 1, 2, and 3. And the way you could read this is the probability I'm more than epsilon away from my mean is less than or equal to 1 over epsilon squared times whatever my variance is, sigma squared. And the kind of fourth way is I could write the complementary version of this. And the complementary version would be that the probability that x minus mu less than or equal to epsilon is bigger than or equal to 1 minus sigma squared over epsilon squared. Not necessarily the most useful. We'll see that in form 3 is very useful. We're talking about convergence. But you'll see Chebyshev's inequality written in basically any of these forms and a couple other kind of simple versions of it. But it's all talking about if you're some number of standard deviations away from your mean, what gives you some bound of the probability. Okay. Before we move on to convergence, we can do one quick example of Chebyshev's inequality. Okay. So our example is that let x, we're going to look at some manufacturing process. So x is we're going to look at manufacturing nails, and x is going to be the number of nails in a manufactured box by some nail factory. And I don't know pretty much anything about the distribution of these nails, but I do know that mu, which is the expected number of nails in a box, is 1,000, and this has a variance, sigma squared, of being 25. And the question is, what is the probability that the number of nails I see, x, is between 1,006 and let's say 994. So one way of saying is that x is, this is kind of an abuse of notation, it's like 1,000 plus or minus 6. You could think of it that way. So what's the probability that it's within 6 of what I think should be my mean, which is 1,000 nails. So we can't calculate this directly unless we know something more about x, but we can bound this probability because we have Chebyshev's inequality. And so in this case, sigma squared is 25, so sigma is 5. And so if we want to look at the probability, that would be 994 less than or equal to x less than or equal to 1,006. We could write this as the probability that x minus 1,000, its mean, is less than or equal to 6. And this is almost in the form of Chebyshev's. We could divide through by sigma, which is 5, say x minus the 1,000, which is the mean, divided by 5 is less than or equal to 1.2. And Chebyshev now tells us, so this is at least, so this is by one of the form of Chebyshev's, says that the probability that the number of nails is within 1.2 standard deviations of my mean, 1,000, is at least 1 minus 1 over k squared. In this case, 1.2 is acting as my k. So remember, let's just write down Chebyshev's inequality. It says that the probability that x minus its mean over sigma is less than or equal to k is bigger than or equal to 1 minus 1 over k squared. So we got it into this form, and in this case k is 1.2, and so if we plug in 1.2, we get 1 minus 1 over 1.2 squared, which is approximately 0.3055 or something like that. So this tells us that the probability I'm within my tolerance, say of 6 nails, is at least 30%. And the probability I've done my thing is at least 30%. Now what you do with that information is up to you, but it gives us some bound without needing to know anything about the random variable except its mean and variance. And we can bound the probability of kind of tolerances of being within so many standard deviations of a mean. Okay. So that's basically on inequalities. We're now going to move on to talking about convergence. And this is what we're going to talk about for the rest of the class. Convergence of random variables. So we basically done a whole bunch of algebra with random variables and transformations and functions of random variables. And so now we're going to try and start doing some calculus of random variables. And so in, say, a second semester calc class, a calc 2 class, you talk about considered, That's not how you spell considered. You considered things like xn converging to x, where xn and x were some real numbers. And now we're going to play this same game, but we're going to consider x n converging to some x, where the xn and the x are random variables. So that's going to be the topic. And the first thing to remember when trying to, so we're going to talk about some different notions of convergence of random variables. And so we have to define what we mean by convergence of random variables. And one of the very useful ways we can, or kind of the most basic way we can talk about convergence is we can recall that a random variable is a function. And so if we have some sequence of random variables, some x sub n's, these are functions from some sample space to the real line. And so is whatever our limit is, it's also going to be a random variable, and that is also a function from some sample space to a real line. So we can consider convergence of random variables by just thinking about convergence of functions. So one solution, which is not the only way to consider convergence of random variables, but one solution is consider random variables as functions and talk about convergence of functions. So let's talk about convergence of functions. So I'm going to give one, there's a lot to be said about convergence of functions, and if you take an analysis class or a functional analysis class, you definitely talk about these. I'm going to talk about the most basic form of convergence of functions. Convergence of functions, pointwise. So this is called pointwise convergence of functions. And if we have some sequence of f sub n's, so f sub n's, n goes 1 to infinity, so it's a sequence of functions where each f sub n is some real valued function. It goes r to r. Then we say that the f sub n converge pointwise to some other function f, where f is also a real valued function, if for any number, if we plug in x into each of our f sub n's, they converge as a sequence of numbers to f at x. So this is called pointwise convergence. The idea is, so this convergence here is convergence as a sequence of numbers. And that is extensively talked about in Calc 2. You talk all about sequences and series, and you talk about sequences of numbers, convergence of them, lots of properties. And so we basically throw back onto that and say, well, we're just going to say functional convergence is if for each individual, instead of saying for any, this should be for all x and r. For any number I pick, if I plug it into all my functions, that will give me a sequence of numbers, and if I plug it into my limit function, that will give me another number. If for every x, that sequence of values I get plugging into my f sub n's converges to the value I get when I plug in f, we call that pointwise convergence, right? So the idea is that, say, x is equal to 1, then we would look at f1 of 1, f2 of 1, f3 of 1, f4 of 1, and etc. On and on. That will give us a sequence of numbers. So this is a sequence of numbers. And this better converge to f of 1, whatever that is, our limiting function. And if that does, good. Then we say, okay, say, what if x is equal to 2? Then we look at f1 of 2, f2 of 2, f3 of 2, and so forth. So, and this better converge to f of 2. And so on and so forth, so say, etc. It better converge for any value x we plug in, be x1, 2, 1.5, whatever value, they better converge. So this is called pointwise convergence of functions. It is the most basic form of convergence of function. And because random variables are functions, we can basically rename this convergence and get a very simple convergence of random variables. So our first kind of useless definition of convergence is called Shor convergence of random variables. And the definition is we say some sequence of random variables, n goes 1 to infinity, converges to some other random variable x if they converge pointwise. Sorry, no, I should write it out. Pointwise as functions. So we define pointwise convergence by throwing back to calculus 2 and saying, well, we're going to fix the x, and at each x they're going to converge as a series of, the function will converge as a series of numbers. And then for random variables, we're just throw back on pointwise convergence functions, say, well, just treat them as functions. So they're a function from the sample space of the real line. And we'll just say, okay, the xn, if they converge pointwise to x, we call that Shor convergence. And you could write xn converge pointwise to x, or xn converge with an s over it for surely to x. And what this means mathematically is that xn of s converges as a sequence of numbers to x of s, which is just another number, and this is true for all s in my sample space. And that's just our definition of pointwise convergence of functions. But remember that our random variables are also functions from the sample space to the real line. So either of these ways you can think about it, that's what Shor convergence is. Now Shor convergence, although we find it, is not actually that useful of a concept. Probability, as I've said, is analysis where we don't care about events with really small probability. So we're going to define a more useful definition of convergence. And basically it's going to be the same thing as Shor convergence, but we're not going to care about places, about if it doesn't work, if the functions don't converge pointwise for a small enough set, for a set with probability 0. So almost Shor convergence, typically denoted A dot S, almost Shor convergence, we say that these xn converge almost surely to some other random variable x if, and there are a couple ways of thinking about that, if the xn converge surely to x on some set A, and the probability of A is 1. So I'm going to let's take this here as way 1 to define it. That is, we can find some set A where xn of s converges to xn of s for all s in A, and A is some subset of my sample space. It's not the whole sample space, but it's a subset of the sample space. And it's a big enough subset that the probability of A is 1. If I can find a set A with probability 1, where on that set, the xn converge surely to x on this set A, and that set is large enough that it's probability 1, we say, good enough. There might be some small set of probability 0 where xn doesn't actually pointwise converge to x. We're not going to worry about it. It's a small set, has probability 0. So the other way of thinking about this is that if the set where xn, let's write it like this, pointwise with a big cross through it, does not converge pointwise or surely to x, if the set where is some set E, so some set E is a subset of sample space, and the probability of E is 0. So the converse way of thinking about this, and they're strictly speaking kind of complements of each other in the probabilistic sense, is that if I look at everywhere where xn doesn't kind of pointwise converge to x, and that set is small, what I mean by small is the probability of being in that set is 0, I don't really care. Then I'm still going to say xn converge almost surely to x. So that's the major idea. And there are a couple ways of writing this. So notation-wise, we say that xn arrow with an a dot s over the arrow x. So this is read as xn converges almost surely to x. And again, either of these two definitions up here will do. Either the set where it does converge pointwise to x, it has probability 1, or the set where it doesn't has probability 0. Either of those count. Another way of thinking about it is that the probability, if I look at the set S such that xn of s converge to x of s, so this is some subset of my sample space, if this thing is 1, that means that xn converges almost surely to x. That's a very succinct way of writing it. Or converse is that set S where xn of s does not converge to x of s is probability 0. It might not be an empty set. There could be some points where they don't converge pointwise, but it's a small enough set, so we don't really care. So probability is just analysis where we don't care about events with probability 0. They don't happen. Who cares, right? We need to fudge it. So, okay, so let's look at an example of almost sure convergence. Example. So we're going to work with a sample space S that is just the open or the closed set 0 to 1, and we're going to say with let's say uniform density. That is, we're imagining that kind of any subset, the probability of being in a subset of S is proportional to kind of the size of that set in some way. Basically a uniform 0, 1 random variable. And consider a sequence of random variables, xn of s, to be s plus s to the n. And so this is how we define a random variable, and this is for all s in little s and capital S or sample space. This is weird because typically we don't define random variables function-wise. But if we want to show some examples of almost sure convergence, we actually have to think about what's the actual function of the random variable. We don't actually think about it typically as a function from the sample space to the real line, but it is. And so that's our x of n's, and we're going to define x of s, that is the limit to be just S, and that is, i.e., our limit is uniform 0, 1, basically, is what that's saying. Okay. And so the question is, does xn converge almost surely to x? So let's think about it. For s in, let's say 0 to 1, including 0 but excluding 1. If we consider x sub n at some one of these s's between 0 and 1 but not at 1, this is s plus s to the n. And as n gets really large, this is going to converge to just s, right? Why does that happen? When n gets large, as n goes to infinity, we have a number between 0 and 1. S to the n is going to go to 0. You're taking a number between 0 and 1 and raising it to a high power. It's going to get smaller and smaller and smaller and smaller and smaller. Eventually, and the limit is going to go to 0. So s plus s to the n is going to go to s. And that is x of s. And so the first thing we've established is that on the set 0 to 1 excluding 1, this works out. So xn on this set converges pointwise or surely to x on this set 0 to 1 excluding 1. When s is equal to 1, xn of s is 1 plus 1 is 2 for all possible n. This is not, say, going to converge to x of s, which is 1, right? X of s is 1. When s is equal to 1, it doesn't work. So on the set 0 to 1 excluding 1, we have pointwise convergence of the random variables to the limit. However, when s is equal to 1, it doesn't work. But the question is that we wanted to answer is, does our sequence of random variables converge almost surely? And since the probability of the set 0 to 1 excluding 1 is 1, or equivalently, the probability of just 1 is 0, because we're going to have a uniform density over 0 to 1, probability of any individual point is 0. We don't care. Let's say we don't care about just this little set 1 where it fails, and we can say that in this case xn converges almost surely to x, because on everything except for that point 1, which just has probability 0, we do get pointwise convergence of my random variables to my limiting random variable. So we're good. So this shows that in this case we get pointwise convergence. So this is almost sure convergence. Almost sure convergence is a pretty strong condition, and so it can often be very hard to verify. You have to really delve down into kind of the functional definition of what convergence of what the random variables look like as functions of the sample space, which is not somehow we typically think about, and turns out it's a pretty strong condition, having pointwise convergence almost everywhere, or with probability 1. And so there's a weaker form of convergence, which is often very useful, and it's called convergence in probability. That's supposed to read probability. And in this case, we don't have to think about these random variables kind of as functions as much. Our definition of convergence probability is we say xn converges in probability to some limiting random variable x, denoted. So our notation is xn arrow with p over it for probability to x if, here's a condition, if we look at the limit as n goes to infinity of the probability that xn minus x is less than epsilon, that limit is 1, we say that xn converges in probability to x. There's a different notion to convergence than almost surely, and we'll talk about how they're related. Alternatively, we could look at the complement, which is that the limit as n goes to infinity of the probability of xn minus x is bigger than or equal to epsilon if in the limit that probability is 0. That's equivalent. Just looking at complementary probabilities. So either of these two ways are valid ways to think about convergence and probability. So let's break apart this definition. Convergence and probability basically looks at, so this, when n is 1, we look at the probability that x of 1 minus x is less than some value epsilon. And then we're going to look at, for x2, the probability x2 minus x is less than some value epsilon. I should specify here in our definition. So if for all positive epsilon, so you can pick epsilon however you want. If for any positive epsilon, this limit is 1, or the limit that xn minus x in absolute value is less than epsilon is 1, or the probability that xn minus x is bigger than epsilon is 0 in the limit. Okay, so epsilon is any positive number. So if we use our first definition here, first you'd say, okay, pick my epsilon, whatever, some positive number. Calculate the probability that the difference in magnitude between x1 and x is less than epsilon. And then the difference in magnitude between x2 and x is less than epsilon. And the probability that the difference in magnitude between x3 and x is less than epsilon. And you can keep going, right? So you're going to get some sequence of numbers as you do this. And if I look at over n, if I look at the probability that x of n minus x is less than epsilon in magnitude. So this is basically a measure of, so this is a measure of the distance of x1 to x, or the distance of x2 to x, the distance between x3 and x. If the distance between them is, if I fix my epsilon, distance between them, so what's the probability the distance between them is less than epsilon? What's the probability the distance between x2 and x is less than epsilon? Probability x3 and x is less than epsilon. As I do this, I'm going to get some sequence of numbers. And maybe at the beginning it's that the probability is low. So I can have probability in 0 and 1. So maybe in the first couple, the probability that they're less than some chosen epsilon is small, but is 0. And then eventually it's small but not 0. And hopefully over time, if my x's get closer to my x of n's get closer to my x, the probability they're within some distance of each other should increase. And so probabilistically, hopefully, eventually we're going to reach a limit where hopefully in the limit, it may never be exactly equal to 1, but in the limit, this sequence will converge to 1. So in the limit of the sequence of probability calculations, I get 1. So that if I go further about my x of n's, the probability that my x of n is more than epsilon away from then the limit is 0, or the probability that x of n is within epsilon of x is 1. So you can read convergence and probability, kind of the intuition is that for large enough n, the probability that x sub n is the distance between x sub n and x, the distance between my sequence element and the eventual limit, the probability it's bigger than some threshold, whatever threshold, is going to be basically 0. That if I pick n large enough, this thing is going to be small, or the probability that they're close together, though less than some threshold epsilon, is approximately 1. So either way, either when you go further enough out, they're going to be with high probability, basically in the limit 1, close to each other, or with basically the probability they're farther than each other than some epsilon is going to be 0. So in the limit, they should be very close together in a probabilistic sense, and that's why we call it convergence and probability. Convergence almost surely says that eventually this has to be exactly equal to 1. Convergence in probability says the limit has to be 1. So that's kind of an intuition, and that it's going to kind of implies that one of these is more powerful than the other. So for convergence and probability, eventually this limit has to be that the limiting behavior never has to be exactly equal to 1, but the limit this has to be converge to 1. Convergence almost surely says eventually it will hit 1 and stay there. Okay, and so let me write that down. Convergence almost surely says that for large enough n, it is going to say that the distance between these things, if I pick n large enough, that xn has to exactly be equal to x, or probability that, and so the probability they're more than epsilon away from each other is 0, or the probability they're within any arbitrary distance epsilon has to be exactly equal to 1. So that's the difference, and we can be a little more precise. This thing has to converge to 0 or converge to 1 for convergence probability. Almost surely says the limit has to be equal to 1 for a large enough n. So you can, we could say approximately, but what we mean is that it converges. And the theorem is that you can see that the almost sure convergence is a stronger condition. And the theorem says that convergence in probability implies, other way around. Convergence, whoops, right? The stronger condition is convergence almost surely implies convergence in probability. Right? If eventually if for a large enough n, these probabilities are either 0 or 1, then it has to be that kind of in the limit, it's 0 or 1. So I could write this more formally by saying that if xn converges in probability, so arrow with p over it, nope, other way around, sorry, if xn converges almost surely to x, then xn converges in probability to x. So that's the theorem. We're not going to go there and prove it, but it is nonetheless true, and this kind of fact above hopefully will come into it. So we now have kind of two modes of convergence. Convergence almost surely, which is basically just saying point-wise they converge for a set of probability 1, and convergence in probability, which says kind of the sequence, the distance probabilistically. If I look at any fixed distance probabilistically, if I get a large enough n, they have to be within that distance of each other with a really high probability. So let's look at an example. So our example of the difference between convergence almost surely and convergence and probability. Okay, so here's our example. We're going to look at, again, we're going to look at our sample space is set 0 to 1 with uniform density, let's say. And we're going to define a sequence of random variables. x1 of s is going to be s. x2 of s is going to be s plus the indicator that s is in 0 to 1/2. So it's going to be s plus 1 if s is in 0 to 1/2, or s if s is in 1/2 to 1. x3 of s is s plus the indicator that s is in the other set. Let's be careful here and properly define this. 1/2 to 1. So this is s if we're in 1/2 to 1, or 0 to 1/2, and s plus 1 if we're in 1/2 to 1. And then we're going to continue on. x of 4 is going to be s plus, and we're just going to keep breaking it into smaller and smaller intervals. It's going to be s plus the indicator that it's in the set 0 to 1/3. X of 5 is x of 5 of s is going to be s plus the indicator that s is in, let's say, 1/3 to 2/3. X of 6 is s plus the indicator that s is in 2/3 to 1. And I'm going to write etc. So we're going to keep breaking it into, next we're going to break it into fourths, and we're going to have now a series of 4 variables, and this is s plus the indicators in each of those chunks, and so forth. And so the functions here look, so x of 1 is just some value s, x of 2 is s plus 1 if it's in the first half, and s if it's in the second half of the interval. X of 3 is s plus nothing if it's in the first half, but s plus 1 if it's in the second half. And so you kind of have this sequence of random variables in this way. And we're going to define our limiting random variable to just be s, as before. So this is a kind of contrived example. It's a very weird set of random variables, but it's going to allow us to show a difference between convergence and probability and convergence almost surely. So if I want to see if my x of n's converge either in probability or almost surely, let's say in probability, what I need to do is I need to calculate x, absolute value of x of 1 minus x. So let's say, if I look at this, this is just going to be 0, because x of 1 is s, x of s is s. And x of 2 is just going to be, it's s plus this indicator minus s, so x2 of s minus x of s is just the indicator that s is in this interval. And we'll do one more. x3 of s minus x of s is just the indicator that we're in the other half, of my interval, and so forth. So the rest of these, the difference in magnitude is just going to be an indicator that I'm in the various intervals in this 1/3, 0 to 1/3, 1/3 to 2/3, 2/3 to 1, and then 0 to 1/4, 1/4 to 1/2, 1/2 to 3/4, 3/4 to 1, etc. And so if I want to look at convergence and probability, I want to look at, say, the probability. So to establish, which I'm going to show, is that xn converges in probability to x, what I'm going to show is, what I need to consider is I need to consider the probability that each of these things, these absolute values, the xn's minus x, when I look at the probability, so I have to look at this, xn minus x greater than or equal to some value epsilon, I got to show that this thing converges, that the limit of this thing is 0 as n goes to infinity. So I write an arrow with an n over it and say that the limit as n goes to infinity is 0. I do these calculations. So, so let's think about this. So we're going to choose some epsilon between 0 and 1. If epsilon is bigger than 1, then it's always going to be 0. So I'll let you think about that case. It's a trivial case. The hard case is when epsilon is between 0 and 1. So in this case, so let's think about what's the probability that x of 1 minus x is bigger than or equal to epsilon. Well, xn minus x being bigger than epsilon, xn minus x is 0 everywhere for all s. So that's the probability that 0 is bigger than epsilon, which can't happen because epsilon is bigger than 0. Okay. What's the probability that x2 minus x is bigger than some epsilon? Well, let's scroll back up here. What's x sub 2 minus x? This is just the indicator that that s is in 0 to 1/2. So x sub 2 minus s, an absolute value, we have this function of s, and so it's 0 to 1, and our function of our absolute value of difference is just the indicator that we're in the first half. So it takes on a value of 1 over the first half and a value of 0 over the second half. Now, if I have some value epsilon, what's the probability that this difference, which is represented by this function here, is bigger than epsilon? Well, it's only going to happen if it's in that first half. And so if we have a uniform density over 0 to 1, this thing will just be the probability of being in that first half, which is 1/2. And we can play the same game, x2 or x sub 3 minus x is bigger than or equal to some epsilon. And that now is just the indicator that we're in the second half of my interval. And the probability that we're there is also 1/2. And you can similarly kind of play this game as you go along. If we look at x sub 4 minus x, probability that's bigger than epsilon, for the same reasons, you're going to find that that thing is just going to be equal to the indicator that s is in the first third. And so the probability will be 1/3. And if you continue on these, you'll get 1/3 a couple times, and then you'll get 1/4. And these are going to keep decreasing. So the sequence is decreasing to 0. And that's exactly what we want. That is convergence and probability. Again, we have to show that the sequence of the probability that xn minus x is bigger than or equal to epsilon. As n gets bigger, this sequence of probabilities that we can calculate better go to 0. And I'm just kind of making some argument that this thing ticks all the way down to 0. So if we believe that as we play this game, xn minus x, probability is bigger than epsilon, converges as n goes to infinity to 0, then x of n converges in probability to x. Okay, so that's nice. The question now, the second question is, so we've established that these x of n converge in probability to x. The question is, does x of n converge almost surely to x? So almost sure convergence means that if I look at these things as functions, then they converge kind of pointwise as functions over a set A that has probability 1. That is, if A is the set of S in my sample space such that xn of x converges to x of s, then the probability of the set A better be 1. It doesn't work in this case, so the answer here is going to be no. If we consider any s in my interval, xn of s bounces between s and s plus 1. What do I mean? If I picked, say, s as 1/3, let's go back up to our definitions. 1/3, it'll be 1/3 and x is x of 1 of 1/3 is 1/3. X of 2 of 1/3 is s plus 1, so it's s plus 1. X of 3 is s, so 1/3. So 1/3, 1/3 plus 1, 1/3. X of 4 is s, so it goes 1/3, 1/3 plus 1, 1/3, 1/3. But x of 5 is 1/3 plus 1, so it goes 1/3, 1/3 plus 1, 1/3, 1/3, 1/3 plus 1, etc. So it's basically bouncing between its value and its value plus 1. And no matter how far I go in the sequence, there's always going to be some point where it's going to bounce back up to its value plus 1. And so because of how I've divvied up these intervals, it's never going to settle down. So I'm always going to bounce back and forth between s and s plus 1 forever, no matter what value of s I choose. And so that doesn't converge. That doesn't converge. So it won't settle down to x of s, this is s. There's no point, as far as we go out and n, there's always going to be some point where it's going to bounce back up between s to s plus 1 and bound down again. It's never going to settle down to our limiting function x of s. So you cannot say that xn converges almost surely, so we can cross it out to x. Because for any value, for every value, you're not going to get pointwise convergence. Because the probability of our set A here is basically 0. There are no points for which it pointwise converges. Now, it's a fairly contrived example. You can see it's a very weird function. We've chosen it. But in this example, we saw that it converged in probability, but did not converge almost surely. We know if it had converged almost surely, it has to converge in probability, but the other way is not true. So the converse is not true. So this shows that the converse is that convergence, let's write legibly here, convergence in probability doesn't imply convergence almost surely. So our converse is kind of false. We know almost sure convergence implies convergence in probability, but convergence in probability doesn't imply convergence almost surely. Okay. So the last kind of convergence that we're going to define today is going to be convergence in distribution. So there are kind of three main modes of convergence. And the last one is convergence in distribution. And this, I think, is the nicest form of convergence. It's most intuitive to people. We say the xn converge to x with a d. Xn converges in distribution. In distribution. If, and I can write this simply as saying the CDFs converge pointwise. So we can't really avoid this pointwise convergence, but what this means, i.e., is that if I look at the CDF of x sub n at some value little x, this converges to the CDF of x at my value little x. And it converges pointwise. That is, well, I can write it like this for all x. That is the definition of pointwise convergence. So convergence and distribution is the kind of third way, which says that xn converges to x in distribution if their CDFs converge. And next time we'll look at some examples of that.